before we just draw the circuit and try to understand it, it's not simple actually. It's a bit complicated, which I feel. Then we just need to understand it. Okay, so we're just going to do it that way. So the topic for today is differential amplifier. Okay, so let's begin with that. So before I really start with the topic, I'm just going to draw the circuit diagram and then we are going to discuss about it. Okay, so drawing the circuit and understanding it is very important. So let's just draw the circuit, try to understand it, and then probably we can proceed with the theoretical part of that. Okay. If you just have a look at this circuit, you basically have got voltage supply. Okay, when we talk or draw an op-amp, we just simply draw a triangle with the terminals, but here what we are drawing is something which is inside the op-amp. Okay, so what I will do is probably I will start from the beginning. I'll try to draw it in the middle, and once I draw it and you understand the circuit diagram, I think half the work is done to understand how does a differential amplifier work or what is its functioning like. Okay, so I'll try to draw a clear picture here. Okay, so I'll put a resistor here. Okay, and then I can put the resistor here. So now there are two terminals here. Okay, I have to take the output, so I will just put the output on this side. You can put the output on the other side also, not a problem. Okay, and put the output on the other side also. Okay, and then what we are going to do is we are going to draw two transistors here. Okay, so we're just going to draw two transistors, one on this end. Okay, and this is basically, you can say, an integrated circuit. So if I'm drawing a transistor, it means that we won't be able to look into it externally, okay, when we actually take up a differential amplifier, but it's there. Okay, it's there internally, and we have the differential amplifier there. Okay, so see, I have drawn two transistors. Okay, and those two transistors will act as the input terminals. Okay, we have the input either from this end or from this end, based on which we can call them as a inverting or a non-inverting terminal. Okay, so at the beginning probably I'll just take the input from one of the end. Okay, so I'll take the end, this end rather. Okay, so we will have an AC signal or a DC signal. I'm not really specifically talking about an AC or a DC. I'm just going to talk about the amplification of the signal. Okay, so we will have an input and we'll basically do it. Okay, so let me just do some labeling now. I think that is again important. Okay, so you have a voltage supply at this particular end. Okay, and that is plus VCC. That basically helps in the biasing. And then we have got some resistances. Okay, so we are taking one resistance here. We'll just write it down as RC1. Okay, that is one resistance, and on the other side we'll just take it to be RC2. So RC1 actually stands for the collector part. So you see, this is a transistor, so I have not yet put an arrow, so I can just put an arrow here. So this will be an NPN transistor. Okay, you can understand this. So if this is NPN, the other transistor should also be NPN. Okay, both the transistors actually should show similar behavior. What do I mean by similar behavior? It means that their input impedance, output characteristic, all should be something which are similar. Okay, so this is very important in case of a differential amplifier. Okay, so maybe I can just do this. Okay, so we have the collector here, the emitter here, and the base here. I'm just writing it down in small because you already know it. So this is collector connected to a resistor, so it is RC1. Okay, similarly on this end, so we have this transistor. We have got these two transistors, so this is how you begin the diagram. Okay, so you can actually have an input. The first is input. So this part, okay, on this end we can actually consider it to be input 1. So this is input 1. Okay, and on this end, if we are actually doing the connection, this may be considered as input 2. So I'm not really putting any kind of input now because I'm just explaining it in terms of any one input. So if I understand this, I can easily understand this also. Okay, so that's your second input that we have here. So that's input 2. So what do I give the signal? How do I give the signal? I basically connect it to an AC supply or a DC supply, whatever signal I want to give. So let's say it's an AC signal, okay, and I want to actually amplify it. So what you can do is you can actually have a signal here. So this is the signal that actually I want to amplify, okay. So I will just put the result as V in 1. So I could have drawn this circuit diagram before and explained it to you, but you know, as I keep on explaining, as I keep on drawing, I think this will be a bit easy, okay. And the output that you get at 2 points, you can get the output at this particular point on this end, collector end, this particular signal, or you can actually get an output somewhere here on the emitter end, okay. Either way, we are going to look into this, that what difference does it make. So you can actually get the output from these two terminals. So this is one terminal, this is two terminal, and this is the terminal from where I'm going to get the output. You have to just remember it in this way. I think this will be a bit more easy, okay. So you know, these are two transistors, so I have to level them out, okay. So maybe I can call this transistor as Q1 and I will call this transistor as Q2. So in electronics, the first thing is circuit diagram, draw it properly, and I think that will be okay. Okay. So if you basically are going to take the output from this particular end, okay, you're going to take it from here. The signal that you are going to get is going to be amplified, but there will be a phase reversal. There will be a phase reversal. So this is an amplified signal, okay. So this is output, okay. So this may be considered as the output on this end, okay. But then you see there is a phase reversal. The phase has changed by 180 degree, okay. So the phase is changed. So maybe I can just level that also. So when you write it down or draw it in your copy, I think you should just take some space and try to keep all the points in one figure as I'm doing it, because it's no, you know, in one picture you can get the entire image. On the other hand, if you're just doing it from this part, okay, what you can do is we can actually, we need to bias the emitter also, okay. So we can bias the emitter via the resistor. The theory is the same as transistors works, okay. So this is the biasing of the emitter. So this is minus V E E. So this is R E, okay. So this is the biasing of the emitter part. So you see in this particular side, the emitter is common to this. Both the emitters are common, okay. So you know, this biasing can actually bias the emitter. On this side, the collector voltage is common, so this can actually bias this collector or this collector, okay, depending on what application you are having or what kind of circuit you want. You want an inverting circuit or an non-inverting circuit. So on this side, if you have an input, you get a phase reversal, and this is the output, okay. But this is amplified. You see, this is a signal, and then this is amplified. On the other side, if you want to take an output from here, what happens is you can actually have a signal here. So if you just want to measure what is the signal at this particular point, probably you are going to get a signal which is similar to whatever is the input. It will be something similar. It won't be that much amplified, okay. In fact, sometimes it does happen, okay, that the amplitude of this might be a bit less, but it's almost the same, okay. So as soon as you go to the other end, and if you want to measure the output from this particular end, you are going to get an amplified signal. You're going to get an amplified signal, okay. And this amplified signal is actually in phase. In phase. Please understand that this is in phase, this is out of phase, phase reversal. This is also an output, this is also an output. So depends from where you are actually measuring, okay, and based on that you can actually get an inverting terminal or a non-inverting terminal, okay. So you see this diagram looks very complicated, a lot of things are there, so you have to just understand this, okay. And if we just assume that a current IEE is flowing through this IEE, so we have got the emitter current which is flowing along this, and you know this transistor has the same property as this transistor. So the current that flows through this transistor and this transistor are both same. And if we use Ohm's law at this particular point, their addition should give you IEE. Since both the transistors should allow the same current to flow, that means it is safe to say that this part the current would be IEE divided by 2, and on this side also the current would be IEE divided by 2. Okay, so if you're actually drawing the circuit, probably this is the circuit that you need to draw. Okay, and you can level it in this way, but please make sure that you level it properly and image is a bit more clear. Okay, so in general, when we actually draw the circuit or the symbol for a differential amplifier, okay, what you can write down here is this is your differential amplifier. Okay, and then you basically have got two inputs. Okay, this is the input that we have, 1 and 2. Okay, and then on the other hand you can basically have two outputs. Okay, so this is the output that you have, one on this end and one on this end. So this is the output, and on paper we think, okay, this is simple, have to just draw a triangle, that's all. But then, since you're doing your syllabus, it's important to know what is there inside. Okay, and this is what is there inside. Okay, also remember this output, I have just taken it towards this part. You can also take the output, maybe I can just draw it that way, or I cannot draw because it's too much space here. What you can do is, probably you don't use this part, you can just take the output from this end also. This is 1 and this is 2. So it will be the same. Obviously, you're going to get the same result. Okay. So in some books, what they do, they use it this side. I'm using it this side. Okay. So it's okay, no problem. Any of those sides, you can consider this to be the output. So this is the circuit diagram for the differential amplifier. Okay. And before we explain its working, okay, we are going to have a very brief explanation of its working. Even before we explain the working, it's important that we understand the circuit diagram. And you see, it's a bit complicated. Okay, it's not very simple, but then I think you should be able to understand this. Okay, so as I keep on writing, I'll probably explain it once again, but then let me just write down few points about oh sorry, enter press ho gaya. Acha, so as I keep on writing, okay, what I'm going to do is I'm going to probably explain you the different parts again. Okay, so the first thing first, draw this circuit. Okay, so all of you should be able to draw this circuit. Okay, okay, so let's just write down some points here. Okay, so the first thing is differential amplifier. Is it a two input terminal device or a one input terminal device? It depends on the application. Okay, so in general I can say differential amplifier is uh, two input. It has two input terminal. Whether you use them or not, it's a different thing. Terminal device. Okay, and I think yesterday I already told you that what do you exactly mean by differential. You are taking the difference between the two inputs. You are taking the difference between the two inputs. Taking the difference between the two input has great advantages, and that is what we are going to explain. Okay, let me write down the points and then I'm going to explain this. Okay, it's a two input terminal device using at least two transistors. So it's not that it will use only two transistors. There might be a number of transistors which are getting connected here. Okay, cascaded system. Okay, and there are two output terminals. So with the same signal, you can actually get an inverted signal or a signal which is in phase. Okay, two output terminals. Okay, so please refer to figure whatever I am explaining, and then you can easily understand this. Simple. Okay. So this differential amplifier transistors, okay, I just use DA again and again. Differential amplifier transistors are matched. Okay, they are exactly matched. If they are not exactly matched, there will be a lot of distortion in the signal. You are not going to get an amplified signal, which is the entire aim of this amplifier. So it's important that both the transistors are actually matched. Okay, so they are matched for what? For same characteristics. You can make exactly two transistors. You can have the same component, they are same characteristic, input and output. So by characteristic I mean input and output characteristics. What does it mean? It means that it should have the same pattern or same values for the input voltage and input current, and the output voltage and the output current that we get. Okay, so this is very important. Characteristics you understand. Okay, RC1, which I have written, must be equal to RC2. Okay, this is another point. This is a part of the transistor being having the same characteristics. Okay, please use sentences when you do this. Okay, so in general we can say that this DA circuit So there are two circuits here in this particular example. So if you take this only this transistor, this is one part of the circuit, this is one part of the circuit, this is both of them are actually identical in nature. Okay, so DA circuit are symmetrical. This is very important. Transistor matching properties are very important for differential amplifier to work. Okay, due to this matching, the DA circuit are symmetrical due to this matching. Okay, that is important. Let's write down one more point. Okay, the third point is signal. So this is already drawn in the picture. Signal to differential amplifier. So how can you apply a signal to a differential amplifier? There are two ways. Okay, which are the two ways? This is one. Okay, we can write this. This is one way of giving an signal input, or this is the other way. So either you can give it through this terminal, or you can give it through this terminal. Okay, so this is the point. And what about output from DA? Output from differential amplifier, again it's two ways. So you see, you can take an output either from this end one or this end two. Okay, so you can both ways you can actually get it. Okay, so based on this we actually call them as single-ended. So I am writing down these words and sentences because I might ask you a question for objective mark points, okay, like 2 marks, and then I might ask you what is a single-ended input arrangement in a differential amplifier. So you can easily answer that arrangement. Okay, so this is a single-ended input arrangement. Okay, what does it mean? That it is signal to, sorry, one end, okay, and other end is grounded, and other end is grounded. So in this particular case, maybe we can ground this side. This is not grounded, please remember this. Okay, this is the signal that we are applying. So if you are applying a voltage signal or a current signal, and you basically are grounding at this part, okay, because this is 0 and this part might be the voltage is more, so the difference is the voltage that you are applying as an input. Okay, so this is not grounded, this part is grounded here. Okay, so if I draw it, but I'm not drawing it right now because I'm not mentioning here whether it is a single-ended or double-ended, but this is a circuit which you can draw. Okay, so this is there, and then you can actually have a dual end or double-ended input arrangement, dual-ended or double-ended arrangement. So in this particular case, dual-ended or double-ended, you are going to apply a signal to both the ends. Okay, ended input arrangement. Okay, so you're going to apply a signal on both the ends. And what about output? You can get the output either from this end, which will be actually opposite in phase, or you can actually have an output from this end, which will be this phase, in phase. And you can have two signals, one is this, one is this, and both of these signal might vary. So you might have a voltage of 10 volt on this part, and you might have a voltage of 3 volt this side. So that means the difference is 7 volt. So that 7 volt will be amplified on this end, you will get the output. Okay, so this is the circuit. Okay, and these are the points that you should know. Okay, I have to write down one more point, so I'll just make it a bit smaller. Okay, I think you can still read it. It's okay. Okay, so what happens is, in general, okay, generally DA is operated, okay, for single-ended output, so single-ended output use of Opamp or the differential amplifier is quite popular. Okay, so maybe you can take this point, but this is just a normal note, you can say. Okay, so this is how we are talking about the differential amplifier. Okay, so the construction part would be the drawing this image, okay, and drawing this image correctly, important, and then probably you can just explain these points, take up these points and explain it. Okay, but it's slightly complicated, so I'll probably explain it from the diagram again. These points you can note down, but in the meantime I'll just explain it from the diagram. The first thing is, you have got a differential amplifier, so you have to look into the op-amp part. Okay, how does it look in a normal symbolic way? So you put the symbol, you have got two inputs and you have got two outputs. So in this we have got these two outputs, and this is one input, this is the other input. Both these inputs are actually connected to transistor. If this is an NPN transistor, this should also be an NPN transistor. If this is a PNP transistor, this should also be a PNP transistor. and both of them should have the same characteristic property. What do you mean by characteristic? It means that if you plot a graph between voltage and current, the values, okay, or the peak, okay, or the maximum value or the saturation point, all should match with each other. Okay, so you know, whenever you say it's a characteristic curve, that means you're plotting a graph between voltage and current. Okay, and then what happens is I am applying an input signal. So I can apply an input signal on this end or in this end. So in this case, I'm considering it to be a single-ended input arrangement. So what I have is basically an AC signal here, and since it's an amplifier, the output should be amplified. So I should have a greater amplitude. So I can have the output either at the collector end, or I can take the output at the emitter end. So if I take the emitter end output, this will be the output here, which will be more or less same, and this will be fed into this emitter. Okay, so this will basically act now as a common emitter transistor. So if it is fed into this emitter, okay, and this already has got some charge carriers in it, this will actually help to amplify the signal, and we actually are getting an amplified signal which is in phase with this. So if you take it here, you get it in phase on this end. Okay. On the other hand, if you are going to take it on this end, okay, we are going to get an amplified signal because you know the signal is passing through the transistor via the collector. Okay, and if you can recall, emitter will emit the charges, okay, and collector will collect it, and the collector end is always the output end because it is collecting. So that means it will have more and more charge carriers there, okay, because of biasing and all the other factors in a transistor. So we are going to get the signal on this end, on the collector end. Here also we are getting the signal on the collector end. So please remember, if you are amplifying the signal, you should get it on the collector end. So I'm getting it on the collector end, and that signal is getting amplified. But since it is fed in this particular direction, we are getting a phase reversal. Okay, we are going to come to that point later. We are getting a phase reversal. So it starts from here, it will basically be here. Okay, so there is a phase reversal of 180 degree. So this is what you should know about this circuit. Now what I will do is I will probably just reverse everything here, okay, because you know I don't want to write these things again, so I just want to explain it here. This is very important. So let me just rub this off. Let me say I'm not giving an input at this end. So I'm not giving an input at this end, okay, and this is your input 1. Let it remain as input 1, and let me just remove the signal from this end. So I don't have a signal anymore, okay, so I'll just connect it directly. I'm just connecting it by a wire, let's say. Okay, so connecting it, no signal on this end. What I'm going to do now is I'm going to give a signal on this end now. Let me give a signal at this end. Let's see what exactly I should expect now. I think you can already make it out, okay, it's not very difficult to understand. But then if I am applying a signal on this end, there is going to be some changes. So now the signal is on this end, and then this is my signal. Okay, so what I'm going to have now is I'm going to, let me rub out this, and then on this end, if you are going to measure the signal, you are going to have a phase reversal. This will become out of phase now. Okay, so maybe I can rub this off. Okay, so for you have to draw another circuit diagram. Okay, don't make a hodgepodge on the same diagram, it will be very confusing for you. Okay, so now what happens is if I'm going to take the signal on this end, I'm going to get a phase reversal. No doubt it will be amplified, but I'm going to get a reverse phase. So this is the output that I'm going to get on this end, output. Okay, if I am giving an input on this signal. On the other hand, what happens here? What happens here is, okay, so on this end I'm going to get a signal which will be in phase. So this end I'm going to get a signal which will be in phase. So the logic is the same. The only thing is which end I am applying the input signal, and based on that I'm going to get a phase reversal or not a phase reversal. Okay, so this side I'm going to get in phase now. So if you are applying a signal on this end, on the other end you are going to get a in phase signal. Okay, so this is how our differential amplifier is constructed, and these are the points that you should actually remember. Okay, so this is important. So probably operations is something which we might not be able to do it today, okay? But then I would just like to give you the advantage of using a differential amplifier, okay? So the next topic is advantage of differential amplifier. What are its advantages? There are in fact a number of advantages because of which this device is usually used, okay? So before I draw the advantage, let me just draw another circuit, okay? But this time I'm not going to draw the complicated one, okay? I'm just going to take the symbol here, that's all. Okay. So maybe this is your output, and then of course there will be some kind of amplification factor and so on, right? So what happens usually is you are going to apply a signal between the two outputs. Let's say I'm going to apply a signal between these two ends, and let's say I'm going to apply a AC signal. Now you see there is a difference between these two values at these two ends, okay? So let's say this will have a voltage of V in 1, okay, and this will actually have a voltage of V in 2. Okay, these are the two inputs that we have, and then what happens is there will be definitely some noise, right? If you are having any kind of signal, okay, the chances are if it's an electronic signal there will be some kind of noise, okay? So let this represent the noise, okay? So maybe something like this, okay, and this actually may be considered as Vn, okay, and Vn is nothing but we are considering it to be noise. Now if in a differential amplifier the difference between these two voltages are amplified, so whatever is the noise will be present here also, and the same noise will be present here also. Both of them will have that noise, okay? So if we just consider this part as V in put 1 dash, let's say this will be a combination of the input that we are having, that means the real signal that we have, plus the noise Vn, okay? And here what happens is we have it as V in 2, and let me write it down as dash. It will be V in 2 plus Vn. But on this end, the signal that is getting amplified is the difference between these two, right? So if I want to take the difference between these two, I can simply write it down as Vn 1 dash, maybe let's say 1 dash is greater. I just take the difference, so I can take a mod also, in 2 dash is equal to nothing but V in 1 minus V in 2. See this, the noise gets cancelled, okay, because you're subtracting one value from the other and you are finding out the amplification of the difference between these two signals, as a result of which if I subtract this from this, the noise gets cancelled. So you know this is a very good advantage of using a differential amplifier, right? So if you just look into the V output, we know it is nothing but the amplification factor that we have, okay, by how much it can amplify into V in 1 minus V in 2. So you straight away see that the noise is not taken into consideration when amplification is done. So the output signal is going to be very clean, okay? And this is it straight away put forward, right? It's very easy and you can understand this, okay? So what are its advantages? Probably I'll just list down 2, okay? And then maybe I can give you it as an assignment to find out some more advantages, okay? Okay, so no noise at the output. We also need to have that assignment for electronics, huh? So probably I will take up some topic and give it to you. No need of coupling capacitors. Okay. So you see, you don't need a coupling capacitor. If you just go back to this diagram, we're not using any kind of capacitors and coupling it, okay? It's not needed. We're doing it directly. And directly the wires are connected to the transistor, so no coupling question, okay? So no coupling capacitors are needed, no noise at the output, okay? We have got integrated circuit altogether where the number of transistors are being combined, okay? Properties of these transistors are being exploited to actually get the amplification factor, and then the signal is finally amplified, okay? So this is how it works, okay? And here I'm not showing you whether it's an inverting or a non-inverting terminal. But in general, if you have a signal like this, and maybe I'm just having one output here written, you're going to have output, okay, where the signal will be definitely amplified, depending on what is the value of A. Another day I did tell you that the A value actually ranges about 10 to the power 5 for many amplifiers. So it's not that you can have 1 ampere and then or 1 volt and actually amplify it to 10 to the power 5 volt. No, that is not possible. There is some restrictions with that. Okay, we're basically going to amplify a signal which is very weak, might be 1 milliampere, 1 microampere. Those kind of signals can be amplified. So when you do any kind of experimental studies and you get a very weak signal and you actually want to know what is the effect of that signal, you first need to amplify it to study it. So for amplifying such signals, we can actually use something like a differential amplifier.